All right, so in the mean field approximation, we're going to replace the actual exchange field with the average exchange field. And this will make things tractable. So let's see how we can work with this. Hang on. Okay. The first thing we'll find is that the mean exchange field is proportional to the magnetization. Okay? So the actual exchange field was proportional to a sum over all the ions of the exchange interaction with ion I times the angular momentum for ion J. But the average exchange field is just proportional to the sum over all of the angular momenta, because the exchange interaction is kind of average. All right, it doesn't vary from site to site now. And of course, this is proportional to the sum over all the magnetic moments of the different ions. And that's proportional to the magnetization. So we can say that the average exchange field is equal to a constant, lambda, times the magnetization. And that's kind of at the heart of everything else we're going to say. The second thing we can do is that we can now see what happens when we add a real magnetic field to this exchange interaction, okay? So we take our ferromagnet and we put it in a real magnetic field. What happens? Well, since the exchange interaction behaves like a magnetic field, even though it's not one, we can say that there's effectively a total field that's just the sum of the exchange field and the actual magnetic field. So we'll say that the effective magnetic field is just the sum of the external or the applied magnetic field and the average exchange field. And so this must be the sum of the applied field plus lambda times the magnetization. Okay? Another useful result. All right. Okay, well now let's see what we can do with these results. Okay. Well, first we can investigate how ferromagnets behave at high temperatures. So remember the simulation? We found that at high temperatures, we go through a phase transition, and above the phase transition, the material behaves like a paramagnet. So what we expect is that at high temperature, our ferromagnet will behave as a paramagnet. So that we can write magnetization is equal to a Curie constant divided by temperature times an effective H field. Okay? The behavior we expect for a paramagnet. But this effective field here we are, can be written in terms of the, we should really write in terms of the effective magnetic field like this. And then we can use what we've learned to try to analyze this. Then the magnetization should be C over T mu naught times the actual applied field plus lambda times the magnetization. And, well, you can see that the magnetization depends on the applied field, but it also depends on the magnetization. Huh. Well, here, we can easily solve this formula for magnetization, though, and let's see what we get. So then the magnetization should be, the magnetization will be m times 1 minus lambda c over mu naught t should be equal to c over mu naught t times the applied field. Okay? Which we can write in the following way. Magnetization is equal to C over mu naught T times the applied field divided by this term, 1 minus lambda C over mu naught T. And then we'll just simplify it to get our result. 1 second. Oh, I'm sorry. 1 second. Just erased our last one. We had let's multiply numerator and denominator by t, and we get C over, I'm sorry. And also let's call the applied field over mu naught, we'll call that H. So then we have C divided by T minus lambda C over mu naught times H. Okay? And finally, let's make a definition. Let's define this term here, lambda C over mu naught, which clearly has a units of temperature. Let's define that as Tc, or the Curie temperature. Then our formula becomes M equals C divided by T minus Tc times H. Okay? So that the magnetic susceptibility, which is the constant of proportionality between M and H, is just C divided by T minus Tc. There we go. So, for ferromagnets, above the transition temperature, the susceptibility is given by this formula. Instead of C over T, that was the old rule for real paramagnets, for ferromagnets above the transition temperature, we get C over T minus Tc. We can illustrate this with a sketch, which is what I've done here. The important thing is that while in real paramagnets, the susceptibility gets larger at low temperature and diverges as the temperature goes to absolute zero, in ferromagnets, it simply diverges when the temperature goes to the Curie temperature. Okay? So above the Curie temperature, ferromagnets act like paramagnets. As we approach the Curie temperature from above, the susceptibility diverges. And then below the Curie temperature, they show spontaneous magnetization. They act like ferromagnets. All right, let's stop here.